Welcome, everybody. My name is Claudio Tesone. I am professor of blockchain and DLT at the University of Zurich, and I am also a part of some initiatives that we have taken here at the University of Zurich related to blockchain-based applications. But specifically as well, we were interested on how new environments can lead to different perspectives to reach broader audiences with respect to education. As part of these experimentations, Metaverse came into being some time ago, and we were really honored to be selected by the Present Switzerland, who is the official partner of Switzerland inside of the World Expo in Osaka in this year. To host a couple of rooms at the virtual expo, and it is with respect to this. It is with respect to this that we have been holding a very prestigious series of talks that I am really proud to continue today of Nobel Prize winners within this environment that is a digital replica of the aula of our University of Zurich. And so I'm welcoming you to this new session. The only thing that I would like to say is those of you that joined the session before 9:30, before the streaming started, if you experience at any point in time a difficulty with the streaming that we are doing in this moment, the only thing that you need to do is to go back to the back part of the classroom and go back to your seat, and the stream will reload again, and the difficulty will be solved because it will be triggering it will be triggering the reload of the system. This would not be possible, actually, this series of events, without the support of MetaPiece, that has been partnering with us in order to have this series of talks. And specifically, I'm really grateful, and I will giving the stage to introduce himself to Yanis Heckbein, who is the founder of MetaPiece, which is a non-profit organization that is focused on education and peace building around the metaverse. So, Yanis, if you want to introduce yourself, would be fantastic.
Yes, hello. Thank you very much, Claudio, for your introduction. And hello, everybody. As president of the Meta Peace Association, it is my pleasure to welcome you to today's Nobel Talk. Today, we have the great privilege to be joined by Nobel Laureate Didier Queloz, whose groundbreaking work has reshaped modern astrophysics and opened a new era in the search for planets beyond our solar system. Science and technology are engines of innovation, and they are also important pillars of peace and transformative development. The Nobel Talks make use of the open and accessible nature of virtual worlds to offer a playful platform for dialogue where audiences from all walks of life across geographies can enjoy the wisdom of Nobel laureates from all disciplines. This project is possible thanks to our dedicated partners. So thank you so much, Professor Claudia Tisone and your team of the University of Zurich Blockchain Center, the team of Present Switzerland, the Swiss Pavilion and Swissnex for our great collaboration, and of course all our supporters who have made this event a reality. Professor Queloz has generously agreed to share his insights with us today, and for this, we express our deepest gratitude. So, thank you so much, Professor Queloz, for your participation and your commitment to advancing our understanding of our place in the universe. And everyone, please enjoy the talk. Before we start, Claudio, give the floor back to you for a short introduction of Professor
Fantastic.
Queloz.
Thank you. Thank you very much for your words, Yanis. And thank you to all of you that are joining today. We have today the great pleasure to welcome a person that has been reshaping the way in which we understand much better our neighborhood inside of the galaxy and perhaps the universe as a whole. Because as a kid, I was very interested in astronomy, and questions, for example, like how many planets were out there, how possible it was for life to exist in other places, um, because direct observation of planets is so difficult, were still unanswered. And now in the last 20 years, 30 years, we have seen a complete revolution, as the title of the talk today is, in this area. We have much better understood our neighbors in the galaxy, and our speaker today has been leading this new knowledge that our humanity has. That's why I'm really, it's for me a pleasure to welcome Professor Didier Queloz, who is Professor of Physics at the Polytechnic Institute of Zurich, ETH Zurich, and the University of Cambridge. He's a renowned scientist for his pioneering contributions to astrophysics. Originally, he got his PhD from the University of Geneva, where he and Michel discovered the first exoplanet orbiting a sun-like star in 1995. This was really a groundbreaking discovery that revolutionized astronomy and later sparked a completely new era in the search of life beyond our planet. In 2019, because of his discovery, Professor Queloz was awarded the Nobel Prize in Physics together with Mayor and James Peebles. Today, he is devoted to his role as head of the Center for Origin and Prevalence of Life at ETH Zurich, where he's leading major interdisciplinary research initiatives focusing on detecting planets that look like the Earth, and in order to deepen our understanding of planetary systems and the conditions that lead to habitability of them. So, Professor Queloz, it is a pleasure to welcome you to the Nobel Prize series. Thank you very much for joining us today.
Well, thank you very much for this lovely introductions. I hope you can hear me well, and I'm glad to be part of this experience. What I will be sharing with you today is, where the change of perspective that has happened in the last 30 years, triggered by the discovery of many planets orbiting other stars. So here we're not talking about planets in our solar system. We're talking about planets farther away, planets that are orbiting other stars. They are very difficult to find, and it took a very long time to develop the technology to do that. And still, we're struggling really to see them, because if you take a telescope and you point to a star, the star is so bright and the planet is so close, so essentially you don't see the planet. You need to use a lot of tricks, and these tricks are being developed these days. There has been some attempt. There is some discoveries on some extreme planet further away for which we have a picture. But essentially, all the planets we know, we have no picture. So how do we know that there are planets? Well, essentially, we use these very simple techniques, which is looking at the star. So we look at the star, and if you have a planet orbiting the star, what you may be able to detect is a slight motion due to the fact that the large orbit of the planet is going to make a tiny push and pull on the stars that will be having a small orbit as well. And if you can detect this orbit, you know that there is a planet. What we did 30 years ago is to develop a machine that could measure with a great accuracy the change of the speed of the star. When you have the change of the orbit, you have the change of the speed, and we use the Doppler effect, which is the shift of the wavelength or shift of the color of the light of the star, to see that. With that, you see there is a planet, you get the mass, and that was how everything started. Now, later, what happened is, if you're lucky, you may be looking at the planet at the right moment when the planet is crossing the surface of the star. You have to be really well aligned to do that. It's called a transit. And in the diagram I'm showing you, this is at that moment there. And if you do that, then you can get something else, which is the size of the planet. Actually, the ratio between the size of the stars and the size of the planet. As we know the size of the star pretty well from different techniques, we can then construct the size of the planet. Now, this is about the techniques, but 30 years ago, we had a big shock, because the planet that we detected, the first one, was not at all the way we thought a planet would be, because the planet we had at that time, the only one we had, are the one in the solar system. And if you look at the biggest one, which would be the easiest one to detect in the sense that the one making the most of the effect on the star is Jupiter. Well, still Jupiter is very small, You need 1,000 Jupiter to have the same mass than the sun. So Jupiter is one of the thousandths of the mass of the sun. But still, Jupiter is making most of the change into the orbit of the sun. It's about 10 meters per second, actually 13. And it takes some time because Jupiter takes more than 10 years to go around its orbit. So the whole year on Jupiter takes 10 years, and the year on the Earth, it's longer because Jupiter is much farther away. But then you can detect that. So we started the program essentially trying to start this kind of detections. And to the big surprise, to my big surprise, to the big surprise of my supervisor, I think we picked a planet like Jupiter, the same mass than Jupiter, but not at all at the distance of Jupiter. That planet was 20 times closer compared to the Earth orbit. So it was a big shock because the planet essentially takes a bit more than 4 days to go around. So it's so close, it goes very fast. And this is all the game started. And it was a big shock because nobody was expecting such a planet. Now, what happened is I would like to share with you the kind of understanding, the physical understanding why nobody was expecting this. And the best way to understand that is to look at how you make a planet. So to do that, I will use a real picture. These are real picture of a planetary formations, which is very young. It's a star in the southern hemisphere, which is called Beta Pictoris. That star is a bit special because we know that there are stuff around the star, which we usually call a protoplanetary disk, that is the material to make the planet. We even know that there are planets. Planet has been detected in this system. And we see the system on the edge. So you have to imagine it's like a big disk, but you see on the edge. So on the top, this is a visible picture from the Hubble Space Telescope. And what you see is a reflected light of all the small material you have in the disk. Well, think about the moon. It's exactly the same. It's just more smaller than the moon. Here we have a lot of materials, asteroids, small piece of rocks, bigger asteroids, and they're all orbiting there, and they reflected the light from the sun, from the star that we don't see because it would be too shiny. And there is a bit of a techniques here, which is called a coronagraph, which is masking the star. That's why you have this big black dot at the middle. It's just a trick. We do an optical trick. Now, I show you that to show you that this kind of a disk is very thin, and all this material are the core material that will be used to build the seed of the planet. So this material will bump to each other, they will glue to each other, and they will gradually build up a core that will have enough gravity to attract a lot of material. So you really build a planet like you assemble like a big Lego game. You just put it together, and it grow. Now, the picture on the bottom is exactly the same picture of the same star at the same scale, but looking at a different wavelength. The wavelength is very special. This one is a wavelength very close to the one you have in your microwave when you want to warm up food. It's called a millimetric wavelength. It's done by a series of radio telescopes, which in this case is in the Atacama Desert. It's called ALMA. And what you see here is not at all the reflected light because you don't see it at this wavelength. What you detect is a gas. And actually, the gas you have here is the CO. It's a carbon monoxide. And what is striking in this picture is when you deal with the gas, you see it's much more extended. It's not that thin. And the reason why, because the gas has pressure, and there is called hydrostatic equilibrium that maintains some pressure, like a bit you have on the atmosphere. The pressure decreases when you go up on the atmosphere, but you have some pressure. And that's why it's much elongated. So the material is not that compact in the gas that you have in the solid material you have on the top. Now, there is another big difference as well in this picture. If you look at the outskirt, there is a kind of a cutoff on the side, where there is a distance from the star where you don't have anything. And it's not because the technology doesn't detect anything. Actually, we do have the capability to detect a very tiny amount of CO on that object. There are really no more gas beyond a distance. And it's kind of a shocking because you see the disk continues on the top. You see the disk is much longer than that. So how come you have no gas? Now you have to think a little bit and remember that the CO is a gas. When it's become cool enough, it becomes ice or snow, if you want, CO snow. So essentially it's snowing beyond this distance. You can do the same with the water. You have the gas, you cool down the water, it becomes snow. And that is a really, really interesting element. That is the foundation of the forming a big planet, because when the gas becomes solid, then it's falling in the mid-plane and it kind of team up with all the material you see on the top. And you have way more material that speed up the formations of the planet when you are at a certain distance out of the star. This is called usually snowline distance. And this is why we have the giant planet in the solar system farther away, Jupiter, Saturn, and then we have Uranus and Neptune, which is a bit smaller. Now, this is really the understanding of the formation of planetary system, and this has been around for a long time, and everybody was expecting the solar system to be the example of the many systems you have in the universe. And then 30 years ago, bada boom, we found this planet that was not at all fitting the story. And I was a big shock, and most of the people for a couple of years never believed it. So it was not easy, I must say, as a young PhD student, just finishing PhD, to deal with that, but I survived because it was real at some point, and then more planet came, and even more planet like 51 Peg came, and we have to acknowledge that we are missing something really big here in the formation of the planetary systems. And what was missing is it's not enough to form planet farther away, the planet has to stay farther away. And apparently this is not a given. You can form a planet farther away, you may have something like solar system, but you may have plenty of other systems that are different. Now, the even more shocking element is the more we have been working the last 30 years, the more we have detected planet on a short distance. And I will share with you the global picture. As of today, what do we know about planet? Looking at very few parameters. The first one is the radius, which is the size of the planet. The other one is the mass of the planet. And against the distance, how far the planet is from the stars. And it's not the distance, it's the period of the orbit that we're looking. So to help you, we have Jupiter, where it would be in this diagram, and we have the Earth. Now, what you do see in this diagram is most of the planets we have detected are different from the one of the solar system. And that is a revolution. Actually, we have found that the solar system is not the example. It's one of the many possibilities. And it's even worse than that. We have zero discovery of systems similar to the Earth. We have none. You see, there is no discovery, whether in radius, which is the transit, or the mass. Now, the problem here, the challenge here is actually this is very difficult to find. And I have to add one more line, which is this detection limit, which is about where we losing the capability to detect planet. It's called a detection limit or thresholds or bias. Let's leave the way we are. Anything on the left can be found, and the closer you approach this limit, the more difficult it becomes. And when you cross this limit, it is so difficult that so far nobody has been able to find anything, with few exceptions really there. Now, it's a fascinating story here, because what I'm telling you is essentially we have been looking for planet since 30 years, but we were incapable, except maybe the Jupiter that we could have detected, to detect the solar system. But still, we found so many. And actually, when you do the math and you try to do the statistics, these are the numbers. And these numbers are telling you what is the chance when you pick randomly stars, which is not so different from the sun, in the galaxy, that you have a planet in that categories. And you see there is few percent. You can pick a planet which has a very short orbit, a couple of days, and a mass of the order of Jupiter, which is the hot Jupiter, what we call the hot Jupiter, because they're very close, they are hot, that's 51 Peg. We have 10% of planet that kind of are like our own Jupiter, while this is a log scale, so some can be really bigger or some can be really closer. So there's a whole range of diversity here. It's not only strictly speaking Jupiter, but we do have. And then we have a set of planets that does not exist at all in the solar system, because these are planets that essentially in a mass and a size regime which is below Neptune's. We call them mini Neptune, usually, or super Earth. And they have orbits which are shorter than about 60 days, which means they are within orbital configurations that would be within the Mercury orbit or closer to Mercury. So between Mercury and the Sun, we have nothing in the solar system. And here I'm telling you that more than 50%, up to 80% of the star, like the Sun, they have planets like that. So the shocking news is actually we may be special. We're not the majority. The solar system is special. I'm not telling you which is super rare because we don't have enough to make the statistics here, but certainly this is not the majority of the system. And of course, this is kind of a revolution because it's like putting now the solar system at the right place in the universe, like we put the Earth at the right place in the solar system and we put the galaxy into the right place in the cosmology. So we are part of this long history of humankind that is part of what we call the Copernican revolutions, because there has been many, that have gradually expanded our view and demonstrated that we are not really the center of the world. And even in terms of the system, of solar system, which is one of the many, and actually we may not be very common, which ask a very interesting questions is whether we do have life is the reason why it's kind of a different system than all the other. And I come back into these questions here. This is part of what's called the revolution here we're dealing with. Now, in terms of astrophysics, it has been a complete earthquake because everything has to be reworked because the theory to explain this planet, we don't have it. There is none have been developed. Nobody thought that it would exist. Nobody thought that you would have an Earth size, an Earth mass planet with an orbit of 2 days, which is technically grilled, is so close that the planet looks like a lava planet, it's a continued lava, or we have mini Neptune, something smaller than Neptune's, and we don't really know what we're talking about. And then what we could do here, we can combine the mass and the size to produce what's called a bulk density diagram that give you a bit of a hint what the planet is made of. And here we have essentially 3 categories, which is these 3 colors that have been showing here. The gray, which is the planet that we usually call giant planet, that would explain very well Jupiter and Saturn. Most of them we have here are in short periods and kind of hot. So they're sitting a little bit above, so they're a bit inflated. They're not exactly fitting the size. Neptune here doesn't reproduce a giant planet. It's a giant planet with far less gas because it never managed to accrete at the time of the formation. That's why we understand it. Enough gas to become like Jupiter and Saturn. So it's a smaller planet. It's called an ice giant and it's denser and it's close to a theoretical line that we call water world. If you take water and you try to make a planet only with water, which is not really possible, you have to mix different components, but just give you an idea that would be there. So these kind of planets that are in this region, they are kind of like Neptunes, but some of them are denser than Neptune, so maybe they have a big core. And then we have a category of planets which are definitely denser than Neptune here, and then we're reaching the green line, which is a planet like the Earth. The Earth would be sitting here, 1, 1. That would be the Earth, and that would be where you would find the Earth. So we do have a substantial number of what we call rocky planet detections, which are all these planets there. We don't really know how they look like. They could be like Mercury, they could be like the Earth. Some of them are more denser. They could have big atmosphere, no atmosphere. There's a lot of possibility, and there's a kind of a gap here if you look carefully. So this is a very active field right now to try to understand what we have found there. Now, what we're doing in this, actually, we try to do a bit deeper and not only deal with the global structure, but try to find out whether we can see something from the surface of the planet that we call the atmosphere. To explain without too much detail how it works, I will show you 3 pictures. Imagine you go in the space station and take a picture of the Earth with your cell phone. That's called a visible light picture. You would see that. It's a fascinating picture. You see the moon in the back for give you the size. You see a tiny layer that gives you the size of the atmosphere. And I would like to remind you that we are living on this planet thanks to this tiny layer, which is no more than 10 kilometers. Here it's bluish because of the Rayleigh scattering that diffuse the blue. This is why we have a beautiful blue sky. Otherwise, the sky is dark. As soon as you go in space, it's dark, it's black and dark. It's nothing bluish. It's only because of the Rayleigh scattering of the solar light that you have it. And then what I want to attract your attention, this kind of atmosphere, very tiny, about 10 kilometers, or let's make it easy, 60 kilometers to the upper layer, which is the ozone layer, and out of the 6,000 kilometers of the size. So we have an atmosphere which is less than 0.1% of the planet. Well, if you take the same picture here in another color, like the infrared, you see exactly the same without the atmosphere. It's exactly the same picture, But in this case, you have the planet, the bare rock of the planet, or the bare surface, which is the thermal emission here, and then you don't see the atmosphere anymore. So the reason why I show you that is the size of the planet actually depends on the wavelength of the color you're looking at the planet. In some cases, you may see the bare rock or the bare surface of the planet. In other cases, you see the planet plus a little bit of something. Now, when you do the transit experiment, you essentially measure the size of the planet. So you can translate these size measurements into composition of the atmosphere, and you can detect whether there is atmosphere and no atmosphere. And if you know exactly some molecules that you may detect, you can even understand whether the molecule is present in the atmosphere. And I show you that with the ozone. This is a wavelength which is tuned to be absorbed by the ozone layer, which is 60 kilometers. And you clearly see we have 60 kilometers difference between the bare rock and then the ozone layer right now here. And then if you know in advance what kind of molecules can absorb, then essentially you get, in this case, a kind of a scan of what is in the atmosphere. So using the transit, we can do way more than getting just the bare size or the bulk size of the planet. We can kind of scan part of the compositions of the atmosphere. And the reason why I mentioned that to you is because it's an active field of research right now, and we have a great equipment that we're using. It's a big telescope now in space, James Webb Space Telescopes, and there is a systematic observations of quite a substantial number of transiting planets to find out what is in the atmosphere. And I want to show you one of the systems that was in the press not so long ago. Is one of these planets that is interesting because it's a mini Neptune. They are farther away from the star in a way the temperature is not too hot and too cold. So interesting atmosphere, which could be seen as temperate. And what we see here, every data point in white corresponds to a measurement of the size of the planet at a different color or wavelength you see here. So you see all the points going up and down, and that corresponds to the amount of light which is blocked by the planet. So it's really the transit, and that's going to block. It gives you the size of the planet. So the size of the planet is changing. There are error bars. It's a difficult measurement to be done, but still you see there are some color, some wavelength where the planet is smaller and the other one which is bigger. Now, if you use a model of the atmosphere, and that's where the tricky part comes, you can guess what kind of molecules is producing these ups and downs and these troughs and peaks you have in the change of the size of the planet. And in this case, they are clearly signs of the methanes and the carbon dioxide in this system. There is an attempt of the DMS, which is a very interesting molecules because it's produced by life on Earth, but nobody really agree on this detection right now. But already the fact that it's methane and carbon dioxide is fascinating because these two molecules cannot stay together. They are reacting, and you would need a special configuration into the planet. Otherwise, you would produce ammonia, and you will end up with something like the Neptunes. But we're not getting into a Neptune. So there is a hint that this planet, which is a mini Neptune, is not like Neptune, but could be a rocky planet with a huge water oceans with hydrogen rich. They are called Iceland planet, and it went to the press and to the news, and there has been a claim that maybe there's a possibility of life on this planet, and you may have picked that a month ago into the press, which I think the community is very skeptical. So I mentioned this to you to show you, I mean, in 30 years, the world has completely changed. So we move from no planet at all to those so many planets, and then I'm telling you, oh, we can detect molecules on this planet. We don't even see them, but the trick with the transit, we can probe what is inside, and I can even tell you something about the possibility of life there. So how is it possible, all that? Because most of these planets are supposed to be too close to the stars, and they're too hot to the stars. Well, we're playing a trick because some of the stars we're looking at are not like the sun. Some of them are much cooler than the sun, and then we even find a system which is orbiting the coolest possible star, you think about it, which is less than 3,000 degrees, which is called TRAPPIST system. So TRAPPIST system, compared to the solar system here, is a system of 7 planets in transit. They all have the size about the Earth, all these planets, but they are in a very short orbit. So comparing with the solar system, they will be within the orbit of Mercury. But what is happening with the system is interesting because the star is not the same than the sun. So the star is much cooler than the sun. So when you are closer, you don't get grilled. It's like the fire, you decrease the fire, you have to get closer to the fire to get the same temperature. When you compute what's called the equilibrium temperature, will give you with some assumptions, the possible temperature on the planet, you realize that there is a similarity between the TRAPPIST system, which is technically closer to the star, but in terms of thermal regime with the solar system. And we can define what's called the habitable zone, which for the solar system is between Venus and the Mars, essentially there. But we do have 3 planets in the TRAPPIST system that are in the habitable zone. Now, it means that we have planets that are rocky, because we know they're rocky, these ones. And then it means that maybe there's an atmosphere on this planet. Maybe there are something going on this atmosphere. And I told you that we can measure the atmosphere. And there's a lot of program I know to focus on this system. Well, so far, no atmosphere has been detected. So maybe they are just bare rocks. There are no atmosphere at all, because the formation of the system is poorly understood. And it's possible that we have the solar system, which is one case, but to end up with a system much more compact like that, much closer to the star, maybe the formation is completely different and something happened and remove completely the atmosphere and there's no atmosphere. But I think already the possibility that we do have system that would be in a thermal regime similar to the Earth, for which we can say they are rocky, and for which we may be able to detect the planet, it's just mind-blowing. The next stage is obvious. Can we look for life? And that's really the bit what the community is doing. So in 30 years, we move from 0 planet to can we look for life? And that's real. It's not just an idea, a philosophical idea, because everybody can have an idea. So when you ask the question, are we alone, whole life there? I mean, this is a question which is already looming around, and there has been a lot of philosophical discussions on this, or has been captured by the church. And all this has kind of a foundation element into the human mind there. But what I'm telling you, this is not anymore about thinking about it. This is bringing facts and evidence about these 2 questions. Now, to understand a little bit what is happening now, I have to go back to the basics, and the basics is actually the Earth. So how can we translate what we have learned about the Earth history into looking for other Earth on other stars in the universe? So to go back to the Earth, one very classical diagram is the story of the Earth as a clock. You know, you start at, if you have a needle steel clock, you remember 6 o'clock is here going around. So the first message I would like to convey to you is the Earth had a complete transformations from the beginning of the formation of the planet until now. And it keeps transforming because it's not a static object. It's a living object. It's a living object because the sun is changing. I mean, it's becoming more luminous in time. And of course, we have a synergy and a balancing between the CO2 cycling and life on Earth, and now the techno-life impact on Earth. So it's an evolving element, but it's always been the case from the beginning. When you think about the formation of the system, the delivery of the material you have at the very beginning when you form the planet is not the material that you have a bit later, because stuff is falling onto the system. The very early beginning, there's a lot of material. And remember this picture I showed you of Beta Pictoris early on, with all this reflected asteroids or matter you have. Well, most of it is going to fall into the sun by the nature of the gravitations and the slowing down of the speed. So, of course, if there is a planet in the and along the way, some of them are going to fall on the planet as well. And look at the moon; it's full of traces of this massive impact. So, a lot of asteroids which tend to be rich in carbon because they made of the CO frozen gas from farther away. So think about this gas there, further away, that this gas has been captured into a cometary body or asteroids. That's why when you have a comet close into the sun, you see this nice tail, because you see all this gas being released because you warm up and then you transform back the icy ice into a gas again. And then it means when you have all this falling material on planet Earth, you bring in a lot of carbon, a lot of element, which will be critical later for the formation of life. And then you settle down and you have a planet which in that case is about 1 billion years old, which is essentially a planet made of the gas and the material you had a bit in the solar system, with, in that case of the Earth, something which is special, which is from the very beginning the same, which is water. So we are the only planet amongst the 3 telluric planets for which we can clearly say the water has stayed the same. Venus clearly have no water right now, and maybe they had it in the past. We don't really know. Mars, I know, lost atmosphere, so must have lost a lot of water there. There's still some there, but lots of water has gone. In the case of the Earth, we have it from the beginning, and it was there. Plus a CO2 atmosphere and SO2 atmosphere. That's really how we understand the Earth after 1 billion years. So after 1 billion years, you have a system with the moon, which is, by the way, formed early on by a massive impact of possibly an asteroid, well, more than asteroids. It was really an object almost the size of the Mars that didn't blow up the planet, but blow enough material to make the moon. That could be in it, maybe critical later for the later evolution of life, but that's another story. And then we have this body. No, something happened after 1 billion years, which is known as a prebiotic moment, where life starts. We have evidence of the stomatolite life at that moment, that life was there after 1 billion years. So the condition that you had at that moment, CO2, SO2, water there, were enough to make life possible. But you see, the planet we had at that moment with life on it, early life on it, is not the planet we have right now, because life evolved and then completely changed the planet atmosphere. And what has massively changed is what's called now, it's well known as the great oxygenations that came later on. You almost have to wait at least 1 billion years before you have a significant amount of oxygen. And the very late oxygenation only happened in the last billion years. And then the great explosions of the Cambrian only in the half billion years. So, but all these have changed the planet. So the reason why I tell you this story is when you look at the planet like that, at different stage, you can look at different kind of atmosphere. And that's what you see on the right, which is the astronomical translations of the story I'm giving you, what a planet like that would look like if you're able to measure the atmosphere in the telescope. In that case, it's a reflected atmosphere, but you can produce also similar measurements about the transmitted atmosphere. And you see spectra, you see absorption line. And what I would like to attract your attention, and the only thing you have to remember here, is this is just tiny differences. This is massive changes. It's not just, we're not looking at tiny detail. We're looking at huge effect. When you have the CO2 on the water, it produces a massive absorption at some of the wavelengths. So it's not about being very precise. It's being just to detect it. And the problem is to remove the Earth to make this picture. So it's really a challenging detections. But once you detect something, you have it essentially. So what I'm telling you is technically, we can study the evolution of an atmosphere of a planet like the Earth on the many other planets that we will find and we have found so far. It's a complete change of perspective because we will be able to compare the evolution not only of Mars, Earth, and Venus, but with almost an infinite number of planets. And this is happening now, and this will happen in the next 20, 30 years. And this is just because we start finding planets. And that's just a fascinating story now, because this is a new evolution that is bringing us to the possibility of life. Now, what can we say about life? And I would like to share with you three elements. It will be really food for thoughts. The first one is this statement of Christian de Duve. I just would like to kill this kind of magic element. Life is magic. No, I don't think it's magic at all. It may be rare, it may be exceptional, but it is written in the fabric of the universe, like said it quickly Christian de Duve, which is, it was there in the equation of the physics of the universe. Like, you have the equation of the physics, you have the formation of the atoms. It's there. I mean, when you form the universe, you don't have very much. What makes the universe fascinating is you enable the formation of stars, and the star are making all the atoms, and then the atoms, with the fact you have planets, start to do the chemistry with some solvent. If you don't have planet, you don't have pressure, you don't have atmosphere, so you don't have pressure, you don't have solvents, you can do the chemistry. So there is a lot of element that goes together, which is the possibility of this universe. So this universe has enabled life, and it looks physically impossible that it's only happening now here. It must have been the kind of a generic situations where life is happening in many different places of this universe, on many different planets, because it's embedded into the equation. Now, the challenge here that we're dealing with is when you talk about life, you see this. This is a tree of life in time. And to read that, you have to start here, the beginning of life, and then you see all the evolution of life, and it's a log scale. And what we do right now is we are looking at this outskirts, just this is where it is today, which is huge diversity, amazing diversity of life going to human. If you look for human, we are here, there today. Now, when you look at that, practically, the big diversification of life happened very late. It's only about the Cambrian explosion here. You have all this diversity. But most of the early stage, the first billion years, you're only talking about bacteria there. So if you look at our real ancestors, they are the bacteria, and the bacteria has been quite immune to anything that has happened on this planet, which is not the case of the slightly more evolved life that is much more reacting to massive extinctions that you see there. But all the rest, I mean, the foundation of life, what is making life on this planet, doesn't see any change. And you see the bacteria, the archaean, all the beginning of the eukaryote, they don't really react to that. So the challenge here is if you want to understand life, you have to go back in time. And it's almost an impossible challenge here to go back in time. And what people are trying to do right now is trying to simulate the condition for early life, possibly to recreate in the lab the origin of life. And what the astrophysicists and the planetologists are trying to do is trying to tell them what are the conditions that you have to create life. What are the ingredients? What do you have on the planets? And we can observe that. We can look at the planet and we can detect this early stage. What I'm claiming here is the astrophysics is going to detect these planets, are going to probe this very early couple of billion years. That will tell you a lot about looking about the atmosphere, understanding the structure of the planet, what has happened there. Now, whether life had enough time to continue the story and to go through a possible global ice age and enable the Cambrian explosions, that's another story. So I'm not claiming that there are this diversification of life everywhere. I do claiming that the beginnings start in many other planets. But maybe planet doesn't sustain life long enough like we had on the solar system. And maybe what makes Earth so special is not the fact we had life, because possibly we had it as well on Mars and Venus. What makes life so special is the conditions for life on that planet has been maintained for so long. And the planet is 4.5 billion years old, and we have maintained the condition for life for 3 billion years. And that may be the very, very special element there. But to find out that, let's observe a lot of planets and find out what are the conditions, whether there is water, for example, whether there are atmosphere, whether most of the planet will be like Venus or not. So this is really the kind of stuff we're going to do. And we're going to do that because we know how to do that. Well, this is the famous blue dot picture, which is a picture of the Earth taken with a spacecraft turning back when it was very far away in the solar system and taking this picture. It's from the 90s. That was the 19th technology here. It was Carl Sagan that advocated for this picture. Now, what I do claim is this picture is fantastic because when you do that, you can study the light from the planet directly. So one day we should be able to do that and to detect this. And that's what it would look like. If you look at a planet like the Earth, you will see the CO, you will see the nitrogen, you will see the water. And for that, if you do that, you say, oh, it looks like the Earth. It's amazing. There's a kind of an Earth twin somewhere in the universe. It's unlikely we'll see this. We may see other things, but at least we will see something. So we'll get real data. And that's just amazing. So I'm telling you right now that not so far in the future, we're going to get real data. And I will know exactly what it looks like in this atmosphere. There are some atmosphere. And the reason why we're going to do that because we are building the next generation of technology. And what we know here is one of these technologies, these telescopes on the ground, which is possibly the only one that can do some kind of work in that direction on only one star, actually, because that was part of the design. And the star that we really want to observe with this big telescope, which is the ELT, it's a 40-meter class telescope, is Proxima Centauri. We know Proxima Centauri is a nearby stars. We know that there are at least one planet, possibly two planets, and there is a lot of development right now being done to promote the idea that let's take a picture and let's look what is in the atmosphere of these planets. And that's just the beginning of the whole generation of equipment that will be the next class of space missions, maybe more telescope like that, bigger telescope like that is going to happen. And one day, eventually, we're going to make a picture. And who knows, we may find out that there's an Earth twin somewhere in the galaxy or not. And that would make us very special in this case. Thank you very much.
Hello, thank you very much, Professor Queloz. Was a fantastic presentation. I think that Shengnan is now also going to share with you the venue as well, such that you get a flavor of how the aula has been looking like in all this time. So it was a fantastic presentation. People, if you have questions, please write them down in the chat. I will start receiving them. I have a question at the galactic level. What are the implications of the because of all the varieties of stars, but also I am thinking in a previous step, that of the formation of planets. Do you think that is it there a kind of a mechanism that has been leading to perhaps newer generation of stars to create the environments to always, or with a very high likelihood, let me put it in that way, be surrounded by planets?
Okay, well, it's a very interesting question because there has been many generations of stars already from the beginning of the galaxies. So the galaxies, I think we consider the galaxies has been formed 1 billion years after the beginning of the universe, which means the galaxies are at least 12 or 13 billion years old. So the sun is only 4.5. So we know the sun is already a very late generations of stars. And every time you have a new generation of stars, you create more chemistry, more complex chemistry, because the stars that produce the chemistry are the big stars, and the big stars tend to be short-lived. So there is an enhancement of the amount of the complex atoms you have at carbon, phosphorus, all these atoms that are key for life in time. So it's pretty clear that maybe early on, the condition was not met in terms of enough elements, complex atoms, and complex chemistry to happen. But since technically, I would say the age of the sun, there must have been plenty of stars like the sun. No, the sun is a fraction of the stars of the galaxy, is about 1%. Most of the star galaxies are smaller than the sun, but we have 100 billion stars in the galaxy. So even it's 1%, I give you 1 billion sun.
Exactly. Good. I do not know. Let me open the. Good. People, remember that if you have questions, you can write them inside of the chat. Okay. Let's wait. I don't know if Yanis, you had another question. Otherwise, I can continue. I could.
There are people waving. I don't know what it means. It's funny. I recognize the place. It's very nice.
Yeah, thank you. Yes, it's our aula.
I know. I've been there.
And we had actually a very crowded environment today. I'm really happy about this. Yanis, did you have any question to Professor Queloz? You are muted now.
Yes, no, so now you can hear me. Thank you very much for this fantastic lecture, Professor Queloz. So, in your opinion, when do you think we will find the proof in terms of years for really other life out there? Do you have a feeling about it, or?
You know, the research is always at the edge. So things goes. It's very rare to get a drastic yes or no. It's not like something very clear, because when you are closer to the knowledge, there's always this uncertainty to deal with. So my guess is progress is ongoing, clearly, and we're developing more and more capabilities. No, the problem is, have we reached the threshold that will be enough to start seeing something? And it depends of the number of targets, it depends of the diversity of life. So maybe today we can consider there is already hints of life if you believe the claim that has been made. No, practically, it give maybe this claim are a bit too optimistic, and they will be, I mean, counterclaim later on. But this claim and critical view, it's part of this progress of science. So you may go 3 steps up, 2 steps down, but globally you move up on the knowledge. So there will be for sure a growing of knowledge. And what makes a difference is when you have a new equipment, because new equipment give you new data. So right now we have a new equipment which is operating, which is the James Webb Space Telescopes. And this one is producing an amazing set of data, and there will be more and more interesting claims. Whether they have enough capability to confirm absolutely, I don't think is going to happen like that. But there will be then a new generation coming up. I was mentioning the ELT, and the ELT is going to produce maybe some more specific answer about the Proxima Centauri system. And then people may find out, oh, this is going closer. So it's about rising up the confidence that we understand what we're seeing. Because remember, we always have to guess. If you get the molecules, you have to ask yourself, does it mean this is life or this is just a planet producing this? So there's always a kind of trade-off. Where does it come from? And it will be gradually a growth of knowledge like we had it in the planet business. It took about 3 years. In the first 3 years of exoplanet discoveries, essentially very few people believed about that. It was a small club. And then things changed, the perspective changed because new discovery came, and then a new equipment called the COPL satellite telescopes started to produce thousands of planets. And then the whole communities tell, oh my God, we have so many planets. And then no, there is not a single institution right now doing astrophysics in the world that doesn't have at least somebody working on that teams. You go back 20 years ago, it was not the case, because the level of certainty, the level of clarification you've reached is such that it's easy to advocate for a program. But still, some of the programs are more difficult than others. They are really front end, and they are much more in the fog. So it's difficult to predict when you're in the fog, when you move one step in the fog, what you're going to get. But I can tell you, we're moving one step. And if there is something that we can detect, we shall detect it.
Yeah, thank you.
Thank you very much. I was looking, there is another question by Mauro that I wanted to read aloud, which is there any technological barrier in space observation that is preventing us from finding planets that are more like Earth twins?
Not really right now. I mean, of course, there's a lot of technology limitation, but that's not a barrier. It's limitation because we limit it and we keep improving things. No, practically we can see avenues where progress can be made. There has been a lot of progress into the space business. So we can launch now equipment much cheaper, and is likely to continue. So we should be able to produce maybe bigger telescopes, maybe using all the robotic and AI capabilities to build up more complex system in orbit or on the moon. And we're talking about the moon base. So that will happen, and it's not breaking a barrier of physics. Like you want to go faster than the speed of light or stuff like that. There are clearly limitations. You are not going to go to another star. It's not going to happen in the next 100 years. Because we don't have the technology, we don't have the physics, you have the speed of light, it's too far away. So there's a lot of problem with that. So it's not going to happen. But then bigger telescope is going to happen. Faster electronics is something we're betting a lot, and there has been a gradual improvement of faster and faster. And why it matter for us is when you start to have faster electronic, you can record the data in a faster way. And instead of being in big telescopes, you can be smaller telescope and combine them together. And that's really what we do in the radio, in the millimetric wave, but we have not done that in the visible light yet, and we're moving slowly in that direction. So the faster electronic would be a massive breakthrough, but about factor 10 about, and that would come maybe with the new materials. So new material being developed for the new electronics may have an impact. But I don't see any really limitation, except that the limitation that as a living body, we have no way we're going to travel into space. We're too fragile. The biology doesn't work, and it's just product. And I think we should stop the idea of transporting people out of the Earth. It's just crazy. It's just too expensive, and this idea to have people on Mars is just nonsense to me. I mean, we should be on Mars, but with plenty of robots and AI systems and exploring systems. But we don't need to be there. We're talking about automation of cars on Earth, and we should be fully automations of systems going into exploring the solar system. So I don't understand why people are completely obsessed by going there. It's just crazy. It's a waste of money. But in terms of development, I think we have an amazing plan, exploring Venus, exploring Mars with robotic facilities, going farther out into the satellite of the giant planet. We have Enceladus, we have Titans, we have Europa, we can study them. There's very interesting chemistry there. Maybe there is some kind of life there waiting for us to be detected. And it would be a shock to realize that there is life in the solar system, which is different, which is not in the same state of evolution because they can't. The state of evolution is very special on Earth, and the one you have on Enceladus, for example, on Titan or on Mars, prevented for this evolution, but maintain still this level of basic life without proper evolution.
Yeah, actually, one thing that you are mentioning now is exactly the landing, the cliffhanger for from my own question. That was, as a kid, I enjoy a lot reading 2001 and 2010, that are these two books by Arthur C. Clarke. And one thing that I liked especially was the description of the life forms that would form in a Jovian planet, or in Jupiter, or either in Europa. And he discusses this. And this lands to two questions. Life forms, if they exist, do you think that they're going to be radically different depending on the environment? And I have a different question that is, I always like very much this process of convergent evolution.
Yeah. Well, it's a very open question, frankly, but there is a couple of facts.
Exactly, but it is just a
couple of facts that people would agree. First, we know only one kind of life form, which is based on the same model. So all life we have on Earth is based on the same functioning mechanism, the same DNA, on the same nucleotide, on the same structure. There is a bit of diversification, but the chemistry is the same. So we have here a problem because this we know, and if we have to find out life, we know what to find. Now, if it doesn't look like that, maybe we will be incapable just finding it because we don't know what to look for. That's the first problem. Now, the second one is whether the foundations of life is likely to be the same. I think there is a possible convergence here on the foundation because, well, there may not be an infinite number of chemistry that enable life, and certainly life as an evolving mechanism that adapt to the change of the system, because the system is changing. A planet is not static. And if you think about the planetary time scale in terms of planetology, it's about 10,000 years. So in 10, 20,000 years, the condition is changing. You have glaciations, you have a change of temperature. So if you have a live mechanism, it has to survive into this massive change. It could be very fitted for a given temperature and conditions. When you start losing water, you start having dry time, you have maybe ice, you completely change. How are you going to survive this? So I think there may be kind of a optimization here, and it's not an infinite possibility. But still, carbon base, the kind of key molecules that are being used, I think it has to be there because I mean, the amino acids are not born by mistakes. They're just optimizations processed by the nature of the chemistry that happened on planet Earth. I know there is a good background theory that explains the amino acids that is related to the available atoms, being with a couple of conditions with water and dry season and dry element combined also with on the surface of the planet with river flow and lake and pond that produce very naturally all the ingredients by the solar radiation. You have the UV radiations you have on the early Earth. So there's a good background on terms of basic element. Now, whether these basic elements are going to move always into that directions, it depends whether it's an optimization mechanism, like you have a kind of valley optimizations of energy, or it's a random mechanism. And nobody knows whether there is the randomness that is part of the process, or it's really an optimization. And there is one best way to make it work, and it's going to survive. So what I like to imagine is life that has tried millions of times. This chemistry, it's just a couple of weeks. So you take a week to make a chemistry, and then after a couple of months, it's dying, and you get another one. It's dying, take another one. So you have a million possibility to the chemistry, and maybe one is going to survive a bit longer, and this one is able to evolve, and then that's one. That's the winning one. I like the idea that life tried many times, and then some of them made it.
Fantastic, yeah. Fantastic. I have another question inside of from the chat. Sorry, which is, you were mentioning that the sun has been becoming brighter. At which time scale does it happen? And I think that the spirit of the question is, has it been happening at the level that even life on Earth has been experiencing this phenomenon too?
Yes, absolutely. So it has been experienced because life is very old. So the sun has multiplied by factor 2 this luminosity from the beginning, and acting life comes really from the beginning. We have life after 1 billion years. So yes, absolutely. No, it happened that the atmosphere have changed, and life didn't depend on the atmosphere for a long time. The atmosphere that we know today is needed for macro life and complex life, the Cambrian evolutions. But before that, the bacteria seems to be immune to that. So you can have a lot of different bacteria that don't really care about what it is. So yes, no, there is something much profound. Is with the continued evolution of the luminosity of the sun, is how long can we maintain this balance with the atmosphere? And there's a couple of interesting models there that seems to suggest, well, we may not be so far from the end. So we know that the sun we're going to burn for 4 billion years. But actually, people are suggesting that the planetary balance may not be sustainable for more than maybe 200 or 300 million years because of the increase of light. Now, everything is kind of messed up right now because we are changing this because of the global warming, because all the gas we're injecting into the atmosphere. So this model doesn't really matter right now. What matters is us, because we're clearly changing the complete structure of the balance, and we don't understand what we're doing. I mean, nobody understands. I mean, we understand the effect, but I think what we're doing is completely out of control right now. So maybe we are just making the conditions that in 1,000 years there will be no civilizations and no human species anymore. Well, the good news is we may disappear, which may be a good idea because we're completely a disaster on this planet. But maybe other species will win, and I'm betting on the scorpions. They're very clever.
Okay.
Okay. Fantastic. Good. It's a very positive message to.
I hope. No, I mean the positive way. I think what is positive for me is I think we are just maybe an exceptional planet, and we have an exceptional species. We have a responsibility, and we just behave like child. And I don't know what to do. I mean, we're just a disaster because the strength is just this extreme aggressiveness we have and extreme creativity. But that's a curse. So the strength is creating the curse. So we have to manage that. We have to understand better the global behavior, and we have to stop being stupid and silly. And then all this war, all this, effect on the planet. We can fix that. It's easier to do that than to go to the moon. But because we're just completely crazy in terms of innovations and power looking, we just can't handle that. So I think we have a serious problem in terms of human behavior to handle all of that. So I'm advocating to spend more money for science of the human behavior, actually, because this is the only way to survive. Is understand better and to try to change it.
Yeah, correct. I think that we see it in a lot of human activities. Actually, I do not want to self-advertise the course, but actually a lot of the things as well happen every time that we invent a new system. We are always trying to overexploit it. Specifically in this course that we're offering now in blockchain and cryptoeconomics is a very good example as well of this kind of predictive behavior that we end up having, trying to squeeze the most of it. Yeah. Good. That's why human behavior is far more important, and how to trigger it and doing proper mechanism design is such an interesting area as well in economics. So, Professor Queloz, it has been a pleasure to welcome you to this series. I'm really happy that you joined us. And I thank also all the people that has been attending this session.
Thank you all. I like looking at you. Like you're very interesting. Next time with the 3D goggles, and I want to see the people.
No, don't worry. We will once we get the 3D goggles, we will call you in if you do not mind.
Goodbye.
Thank you very much.
Bye.
Bye. Have a nice day. People, we stay here. Yanis, thank you very much for the presentation. Next time, one thing, people, is the people from everybody that is here in the thing, we are going to make a little tour through this space and the other, and we'll have a couple of group photos. So you are all welcome to you are expected to be connected only, I would even say. So Yanis, thank you very much for this wonderful
Thank
session
you
as
very
well.
much, Claudio, for this.
You can join us. We will have a group photo here and in another location here in the